Okay, welcome to the second lab of Geology 2017, Geology for Engineers. We are going to look at igneous rocks today. So in this lab, the idea is really to describe some of the keywords that are commonly part of the terminology that is used to describe a variety of igneous rocks. So we're going to look at mostly intrusive rocks, but also we will discuss some of the nomenclature for the volcanic rocks as well. So effusive assemblages. So without further ado, I think it's important to keep in mind some of the key minerals. Really, we have reviewed extensively the mineralogy. So if you look at the cosmic classification here and fractionation sequence, similarly to Bowen, we have the key mineralogy, so the transition in composition of feldspars that you see here on the top with essentially classic compositions like labradorites and going into more alkali feldspars. And these are entirely part of the identification and classification of rocks. So here we have a number of rock types, which is useful to learn because they're the most basic ones, really. So we start with basalt, which is the effusive equivalent of a gabbro, then move into andesites, so diorites for the intrusive part of this classification, and then we move into rhyolites, which are more silicic and also have this transition in the composition of the feldspar, so they will tend to have much more K feldspar in them. So lots of visible quartz and K feldspar will be quite common. Instead, in the basalt, you will rarely see really K feldspar. It's dominated by plagioclase, so your labradorite, for example, which is a calcium rich plagioclase. When we move this way, we tend to increase the sodium content of the plagioclase as well. So this is why we use these terms to name different really solid solutions, which includes calcium sodium transitions in the plagioclase. On this side, we have rather the ferromagnesium minerals. We have talked quite extensively about this other part of the Bowen series, and so Goldschmidt has a similar classification with the transition that goes from olivine, so the ferromagnesium silicate, and then moves into things like augites and amphibole. So we go into pyroxene and amphibole, and then have more hydrated phases. So we increase the amount of volatiles and water available to the structure of the silicates, and we started to develop ribbon-like geometries where we host fluorium or water or other large cations, and this will be hosted in amphibole as well as in strata-like phyllosilicates, so layered or sheet silicates such as biotite. So still iron magnesium minerals, but more hydrated and usually occurring in highly fractionated magmas. The same is true for these other series. So if we look at the oxides, so the spinel family, we have chromites that are more characteristic of early stages of fractionation, so they will be often found associated with basaltic magmas or ultramafic magmas. So you will find chromatites, for example, when you form layered intrusion complexes, and we will discuss about layered intrusion in a dedicated lecture, as well as when we will be introducing mineral deposits that are particularly rich in chromites, such as the Bushwell complex. But yes, chromites will be really part of the early stages of fractionation, so they are more associated with olivine and the plagioclase, and then you have a transition and you go into ilmenite magnetite series, so you increase the oxidation and have this magnetite forming, which is more, in line with this idea of having more hydration and more oxidized conditions for these magmas. And this gives you sort of an overview, a framework to understand that one important concept. Usually rocks have a specific mineralogy associated with them, and so you will need to recognize the minerals that are in the rock to understand what rock you're dealing with. So one simple example is this, and remember, usually in a basalt you will have quite a bit of plagioclase, and also you might find some olivine, traces of olivine, and or phenocryst, more correctly, of olivine, as well as some chromite, and also other minerals such as pyroxene. So augites are quite often present in basalt. The same is true for the other end member. We talked about rhyolite, and we will find quite a bit of potassium feldspar. Possibility of finding quartz is also quite frequent, and so dominantly you have a rock that is more silicic and has an alkaline feldspar that is the dominant sort of phase, and also you will find potentially amphibole and biotite. Quite a bit of biotite is often present in a rhyolite. So you see how the mineralogy can help you with the identification of a rock. If you can recognize amphibole and biotite, and you have quite a bit of K feldspar, and you have a rock that is effusive, well, most likely you will be dealing with a rhyolite. So here we are looking at another diagram that gives us a perspective on the location and positioning of specific rock type. This diagram is particularly important as a summary of how texture evolves and changes depending on the location where you solidify a magma and you crystallize essentially a magma and form a rock. So you have intrusive rocks at the bottom, and quite often these will have characteristic textures, like equigranular textures. Usually you tend to have the crystals or minerals forming crystals will be developing well proportioned, and you have a very good crystallization taking place. So the rock appearance will be as a granite, for example, so here, or a gabbro, in which you tend to have sort of rocks that cool relatively slowly, and you have large coarse crystals that form. So you will be able to see the crystals with the naked eye. Quite often, when you move up in the sequence, crystallization is harder, and because of that you tend to form rocks that are of this fashion, and these are commonly called porphyries. So in this case the crystals that form into a matrix, and so you have a difference in the scale or dimension of the crystals that form. you will form both very tiny crystals that tend to compose the matrix of this rock, which is similar to a cement. So it's a microcrystalline matrix quite often. And then you have larger crystals that crystallize first quite often, and these will tend to be called phenocrysts because they stand out if compared to the microcrystalline matrix. Okay, so there is a difference essentially in the scale of the crystals. Very large ones, your phenocrysts, which you can use for the identification of the rock. So if you find very large phenocryst of K feldspar, as I was discussing earlier, you might classify the rock as a rhyolite. And so you would be up here, you know, in this context, but this is really an exception. So subvolcanic rocks can form porphyric assemblages of this type, which are easier to classify. In this other case, we are rather in a subaerial domain. So we have a lava, and so we have felsic lavas that form rhyolites or dacites, and these will have tiny crystals or tiny phenocrysts of K feldspar that you will need to use, you know, magnification like hand lens to recognize them. So that's probably a key difference between effusive rocks and intrusive or porphyries. So these are all intrusive rocks. In these examples, we tend to have the opportunity to just use our eyes to identify minerals. These are the rocks, rather you need a hand lens to identify the mineralogy. So the extrusive rocks are not exclusively represented by lavas. We have seen when we were talking about volcanoes that we have also a variety of effusive products that are subaerial and explosive, and so they tend to be ejected from the cone of the volcano. And so these are classified commonly using the composition and size. So you have volcanic ashes, pumices, a little bit larger, and then the extensively large bombs. So it's important to be able to identify things based on their morphological characteristics when you're working with these specimens. And we will see that we can distinguish, for example, pumices from scorias of a cinder cone, and usually that is a density related classification as well. So we will talk about that later. So what do you need to consider when you are working with different rocks of igneous nature? Certainly the grain size will be a key factor. So you have seen that already in this initial discussion. A distinction between intrusive and effusive rocks is usually related strictly to the grain size. And effusive rocks usually has tiny crystals and very few phenocrysts. The more you get into a crystallization that is low and deeper in the crust, the larger will be the grain size of your crystals, and the rock will look as what is termed as an holocrystalline rock. So you will tend to have that the rock is mostly composed of large size crystals or phenocrysts. There are other things that we can sort of infer as controlling the size of crystals. Here there is an example that is looking at chilled margins. So it's important to understand that often you can recognize relatively shallow intrusives by looking at chill margins. So if we can effectively recognize a systematic change in grain size for example, an uplight, so an intrusion that is a dike or a seal into a cold host rock, so sedimentary assemblages, for example. In that context, we will tend to have smaller crystals in the chill margins. And so that's a good indication that you are dealing with an intrusion that solidified in relatively shallow conditions. So remember also this terminology here. Usually a phaneritic rock will be an intrusive rock that is coarse-grained. Instead, a basalt, an obsidian, or a dacite, or a rhyolite. We talked a bit about rhyolites with the K-feldspars. These are quite commonly defined as aphanitic, so you have fine-grained cement or actually a fine-grained microcrystalline matrix, which can be glassy if we are talking about obsidians or volcanic glass. And so you will not be able to see crystals really. But there might be aphanitic rocks that have small phenocrysts, but these will be isolated cases. So important to use this terminology when we discuss together during the examination these type of rocks. So I might give you a rhyolite and I will ask what kind of matrix we are dealing with, and if it is a phaneritic rock or an aphanitic rock, and you will tell me that the rhyolite has an aphanitic microcrystalline matrix with the isolated phenocrysts, which are those large crystals that are essentially growing within this matrix. Another important aspect that you will discuss with me is the color. So color is certainly one of the most easily observable features. It is quite useful when we are discussing the composition of the rock. And usually it is mostly conditioned by the abundance of felsic versus mafic minerals. Okay, so the color is largely a reflection of the proportion of mafic and felsic minerals, and this is really irrespective of the grain size. Although in some cases you might have very large phenocrysts that are white in color and they can affect the color of the rock. So it's important to sort of consider also the combination really of factors, and sometimes the phenocryst might be K-feldspar, so the rock might result as being characteristically pinkish in color, which is a good distinguishing factor for also alkaline granites, as we will see. But yeah, in fact, finer grain size rocks will tend to be sort of darker in color. So even if it's a felsic rock, but if it's really fine grain, you might end up having that the rock is quite dark. This is a good example for rhyolites. Sometimes rhyolites are actually black, and this is related to the glass content. To classify the rocks, it's important to, and I mentioned this at the beginning of the lecture, this is really to get you familiar with the terminology that we use. So I might ask you if you think a particular specimen is a melanocratic rock, a mesocratic rock, or rather a leucocratic rock. You have here a definition which is based on the estimation of the percentage. So quite often a geologist will look at a rock and use some height to estimate the percentage. Of course, during the oral examination, you are allowed to use this chart, or I will sort of tell you roughly the estimate of the percentages, or you might guess the percentage and we might have a conversation about that. But the important thing is that you don't call a rock that has 10% mafics, a melanocratic rock. So it's important that you connect the term melanocratic with rocks that are sort of enriched or have more than 75% of mafic minerals. And the opposite is true for leucocratic rocks, which will have less than 34% mafic minerals. So we are in this realm. So these are leucocratic rocks, or you could call a rock that is between 34 and 66, like this example here, a mesocratic rock, and I would be fine with that. So in essence, this phenocrysts will be critical. So the percentage of mafic phenocrysts can help you in defining a terminology for calling a specific rock. So if you tell me that a rock is leucocratic, I will know that already it does have very few phenocrysts, and these are relatively low in percentage with respect to the total volume of the rock. This is commonly called also modal abundance. We have other diagrams that illustrate the same concept for both the mafic and felsic volcanics or intrusives. So if you have a rock that is represented by a crystalline matrix that is felsic, you will use isolated phenocrysts that are mafic in composition to define the rock as leucocratic, but certainly this other example will be more, a rock that is melanocratic because of the abundance of mafic minerals in the microcrystalline matrix, and so the contrary is true in this case for the phenocrysts, which are essentially dominated by felsic minerals, which could be plagioclase for this particular example. So as long as you move through this classification, you can clearly see an increase in the volume of phenocrysts, and so we end up with this end member where the terminology is biased and conditioned, as I was stating earlier, by the phenocrysts themselves. And so here you have that the phenocrysts are actually mafic, and so you will call it a melanocratic rock, and here they are felsic, so it's more a leucocratic rock, and it's exactly the opposite as this example here. So here is the matrix that dominates the nomenclature. Instead here it's rather the phenocrysts that actually controls that. So you will be able to say using this chart that there is a specific modal abundance. So in this particular case, this means that, for example, here I have the 80% of the rock that is represented by phenocrysts, and the remaining part will be the microcrystalline matrix of the rock. So it essentially gives you an understanding of the volume of phenocrysts with respect to the matrix. Texture is also a key aspect of rocks. We will see, especially when we will talk about metamorphic rocks, that texture is very important to unravel the structure, but structure can form also in response to other processes that are more related to the igneous crystallization of an intrusive. And this is commonly resulting in characteristic information that is useful to interpret how the rock formed. So texture is really also a key feature of igneous rocks, as it provides sort of information on the physical condition in which the rock formed. Quite often we have crystalline texture in igneous rock. That's kind of represented by the angular interlocking of crystals, and quite often when you have to describe a rock, you will need to understand if the rock is sort of holocrystalline, for example. So if it does have a relatively high level of crystallinity or rather low level of crystallinity, and we go back to that terminology of defining the rock as an aphanitic rock. So that's commonly falling into also the granularity, so the description of the granularity, which is the size of the grains, but also for texture we mean the shape of the crystals, because you can take minerals like quartz. Quartz might be with a proper shape, so a shape that is related to the symmetry of the crystal, or it could be anhedral, so a crystal can essentially adapt to the shape of other minerals and be represented as an infill mineral. So it could form within a vein, within a fracture, and doesn't really have the proper symmetry. So it's important to realize this concept and to be able to describe this as part of the textural feature of a rock. So I might ask you, for a specific rock, what are the euhedral minerals? So discuss what minerals have a proper shape versus minerals that don't have really a proper shape. And this leads us to understand what is termed the mutual relation of crystals, so how they are essentially interacting. Sometimes you have growth in growth, so cases that show actually the existence of euhedral crystals inside a pre-existing crystal. So if we go more into the details, crystallinity really is defined in two terms. So we have holocrystalline rocks, which are quite often plutonic rocks, and so these will display quite often crystals that have pretty much the same size, and these are visible on the naked eye. Instead, volcanic rocks quite often will be allotriomorph and will have essentially a microcrystalline texture and some phenocrysts which have a different size, as stated earlier. We have also granularity. Granularity will be discussed with these terms. So if you don't see any crystals, you term the rock a glassy rock, and these are obsidians or volcanic glasses most often. But then we have cases in which you can see some crystals that will be fine-grained under the millimeter, between 1 and 5 will be medium-grained, and then you get the coarse and very coarse varieties, respectively between 5 and 30 and more than 30 millimeters. There is an exception, which is rocks that usually form at the top of a magmatic chamber, so in a large intrusive or a batholith. On the carapax, so the top part, many times you have accumulation of separated phases such as CO2 or water or vapor, and this usually allows for the growth of large crystals. So very coarse grain textures are common, and these are called pegmatitic textures. So if you have usually crystals that are on the order of 30 millimeters or more, you can start to call these rocks as pegmatitic, and you will also give it a name that is related to the composition of the rock. So I could call, for example, a granite a pegmatitic granite, and I mean that the crystals that compose the granite are quite large, exceptionally large in some cases. Mineral size distribution are terms that are used to describe the inequality in size. So if the crystals are all the same, we commonly call the texture equigranular. So rocks that are equigranular essentially have minerals that are about the same size. If that's not the case, like in a volcanic rock, the rock will be called inequigranular. Again, I might ask you if you think a specific rock is equigranular or inequigranular. So it's important to understand what this means. The same is true for these other terms, so allotriomorphic and apolitic. So they usually are used to describe rocks that are anhedral and have equigranular textures. So that means that you don't have really a shape. So a volcanic rock like an obsidian could be called an allotriomorphic rock, as well as a microgranite. So usually apolitic dikes form a relatively shallow conditions, and they don't have enough time to crystallize. So you tend to have very fine grained textures that are equigranular, and this would be a good term for the classification of an applied. Rocks with subahedral equigranular textures are quite often described as epidiomorphic or granitic textures. So a subahedral usually is a rock that we will see is represented by partly regular and partly irregular crystals. By irregular, I mean the morphology of the crystals. There might be cases in which the crystals are partly developed, and so you have both a combination of euhedral and also anhedral minerals. And finally, you have the euhedral. Euhedral is rock that are panidiomorphic, and so rock that have equigranular textures that are represented entirely by well crystallized minerals. Most commonly, so these were all equigranular rocks. If we look at inequigranular textures, we most often think at porphyries. So porphyric rocks, we saw some examples at the beginning of this lab, tend to have a microcrystalline matrix with very large very large phenocrysts. So that's really the golden standard for porphyries. Porphyries are very important also in exploration, so it's important to be able to recognize them when we are looking for mineral deposits. So in economic geology sense, porphyric rocks are quite important because they tend to be associated with large ore systems, and these are the porphyry systems, which are essentially dominated by either base or precious metals, so copper or copper gold or copper moly associations are quite common in porphyry systems. And this is because, when you are in the shallow environment, you will have a lot of liberation of fluids, so hydrothermal activity is promoted, and that's why you have this linkage between porphyric magmas and the formation of large accumulation of base metals or precious metals. So remember, when you have large crystals, these are termed phenocrysts, and then you have vitrophilic textures, so where the phenocrysts are embedded in a glassy matrix. So sometimes you will find obsidian that has particularly well crystallized quartz, for example, which is called cristobalite, a particular phase. So it's a high pressure temperature phase of quartz. Well, in that case, you could call it a vitrophilic texture. Other cases, the phenocrysts will be clustered, and they can be clustered at the bottom of a chamber, and so you call it a cumulate or cumulophilic texture, because you have essentially agglomerates of clusters of phenocrysts. This is also quite common in glomeruloporphyritic textures. We will see some example of that later, and so this renders usually these rocks particularly interesting because of the beautiful assemblages of phenocrysts, which render them quite interesting for industrial applications. So recapping on some of the terminology, we have some visual examples now of this distinction in quite often used in either equigranular or inequigranular rocks, in which we go from euhedral to the end member that is anhedral, and we have this intermediate sort of subhedral case. And you can see here the example. I mean, we have cases in which all the faces of a crystal are relatively well developed. And so we would call this an euhedral phenocryst, or other cases in which we have that part of the crystal becomes irregular, so we have a squared plagioclase in this example that is partly developed with its own symmetry, so that's a section of a mineral in reality. And then we have that this part is more lobated, so it's more like this example in which you have more curvilinear boundaries, and so this is commonly called a subhedral crystal. Then you have cases like this, in which you have very irregular margins of this phenocryst, and in this particular case it would be an anhedral example. Here we have these clustered textures in which you have cases in which the phenocrysts are well separated, so they don't touch themselves, but other cases in which you form cumulophilic textures, like this example here with these mafic minerals that appears as being accumulating at the base of a magmatic chamber, and so they are clustered and piled essentially one on top of the other, and that's also a good indication of how this crystallization took place. So important to be able to identify really the different morphology and texture, and being able to describe the shape of the phenocrysts, and also identify the composition. In this case, we can see that the phenocrysts are pinkish in color. Quite often this is a feature of K-feldspar because of the inclusion of iron in the structure of the K-feldspar, which progressively with the crystallization get expelled from the structure and will tend to oxidate. So oxidation gives this characteristic reddish color of micro, essentially very tiny quantities of iron oxide are present. And these are other examples, which this will be likely because of the losange shape and other features. This will be likely amphibole that has precipitated in this particular specimen. And so we go back to this distinction between alkalic magmas versus more plagioclase rich magmas that contain also quite a bit of amphibole, which would be, classic of tonalitic rocks, which we will be seeing in the later classification when we have to give a name to the rocks. So mutual relations are also important when you discuss texture. We have different examples here. So we have this first example in which we have a plug of biotite in a rock that is surrounded by another mineral. So these are all phyllosilicates, and you can see here that partly this biotite has been recrystallized into chlorite, so that gives you an indication of the relative age of these two minerals. Quite often biotite will be younger because usually one mineral surrounds another is actually younger. So the core here is older essentially of the chlorite. So the chlorite is growing after on top of the biotite. So relationship of crystals can be used to infer relative age of crystallization. Also, usually mineral that form first quite often is the first to form, and this is a good example here with this intrusive rock. So that this is looking like an alkaline granite, and in this case this pinkish mineral are the largest phenocrysts, and these are usually the first to crystallize because of that. So larger size and very well developed phenocrysts tend to come first, and then you have that the remaining space is filled with anhedral minerals. In this case these are mafic minerals, which could be either amphibole or pyroxene. Okay, so if large and small crystals are present, usually the big ones will be the first one. So the size and the eohedral nature will help you discussing the relative age. So the order of crystallization is also usually a good indication of rocks that are following the Bowen sequence, and so you would have to expect, situations in which you tend to crystallize firstly the mafic phases, and then you progressively crystallize the other more felsic and fractionated phases. And so in a case like this, it is quite commonly easy to find K-phosphor in association with abundance of biotite and also amphibole. So it's likely that this mineralogy will be really a mineralogy that is characteristic of the late phase of crystallization. Another important aspect in this case are the overgrowths that you can recognize in some of these phenocrysts, which are a good indication of the evolution of the phase of crystallization on this particular granite. So that's also an indication that you had firstly a K-phosphor rich crystallization, and then you have potentially a transition into other compositions that could be more either this could be represented by either quartz or a rather more sodic phase of feldspar. More terms. I mean, when we have ingrowth of other minerals, we form what is called a poikilitic texture. So these are just some examples. So you have here a crystal of pyroxene, which you can recognize because there is some cleavage present. So you can see a set of parallel fractures and they form high angles, so almost 90 degrees. And that's kind of characteristic of rocks like pyroxene, so minerals like pyroxene. And yes, there are numerous inclusions in these, and these are actually not really displaying any interesting cleavage. So you can use these as a sort of diagnostic tool. And so you have pyroxene with inclusions that could be likely represented by olivine. Okay, that's because quite often you have cases in which you have the olivine forming in conjunction with pyroxene when you have a ferromagnesium rich rock like basalt or an ultramafic rock. Some of these other minerals could be still other pyroxene because of these high interference colors. This is a thin section and we have crossed the nickels, so we are looking at some interference colors which can be also helpful with the recognition of some of the mineralogy. But this is a little bit too advanced. Just to keep in mind the fact that in some minerals you might find inclusions, and these inclusions are usually represented by other mineralogy, which you can then represent or describe as a poikilitic texture. In basalts, we have also this term, so ophitic. Ophitic textures are very similar to what we were saying before. So when we have crowded assemblages or lats of plagioclase, usually you call the rock as an ophitic rock. So a glomeroporphyritic basalt, for example, will be an ophitic rock. And then we have granitic rocks with graphic granites, which we have some examples later to show as well. So these are other terms that we can use. So this is an example from Middle Fork. So it's essentially in Washington, in USA. It's basalt, and it does have this characteristic cereal-like texture. It's kind of interesting how it forms. You tend to have that the density is a key player in this crystallization process. So quite often density will form layers of stability for minerals. So you tend to have that minerals essentially float at a specific level in a magma. And in this particular case, since the plagioclase is actually low density, it will float on the top. So this is why I'm talking about the Cheerios, which is, like cereals on milk. They will tend to float at the top and they tend to coalesce together. And this is what is happening also for these feldspars. They form these nicely elongated crystals. You can see some elongation here. And so these bladed crystals tend to accumulate at the top of the lavas, and they form these characteristic clusters. So that's commonly a porphyric texture, but you can call it also a glomeroporphyritic texture as well. This is another example of characteristic texture you might encounter during the examination, and these are called graphic granites. So the composition usually is enriched in feldspar and quartz. So that's the distinguishing factor for these rocks, the abundance of quartz. Remember that if you are dealing with a gabbro or a more mafic granite, you don't call it a granite, you rather call it either a granodiorite, a tonalite. So it's a different really beast, or a gabbro when you start to have 50% pyroxene in the rock together with 50% plagioclase, and you lose completely the quartz. So this is why you call this rock a granite, because you can see here a solution of quartz and feldspar that are tightly crystallizing together and forming this characteristic texture, which has been compared to the cuneiform writing of ancient populations. So this is really because of this triangular sort of or cuneiform geometries that you can see, and this is the quartz. You can see it because this is in cross nickels, so it has high interference color if compared to the gray color of the feldspar. And so that's kind of unique and quite characteristic. Usually this happens really in highly fractionated magmas, where you have a lot of quartz and a lot of hydrothermal processes taking place. It's also quite indicative of abundance of volatiles, and in fact it's actually important also for the prospection of mineral deposits. So remember, these are a solution, so related to essentially rapid quenching of magmas. So if you have fluids that are cooling down rapidly, an intrusive rock, you may develop instabilities, and you tend to have that you have a separation, rapid separation, in which you form these exsolution textures that are essentially separating quartz from feldspar. So how to describe your igneous rock? We are now at sort of the end of this lab. We are summing up or providing a summary of the things we discuss really. So when we will discuss a rock together, an igneous rock, I essentially will ask you about color, mineral composition, texture, and hopefully you will be able to use some of these terms to describe what you see in the rock. The last aspect is really to give a name to the rock. So based on the mineralogy, remember the Bowen sequence, we will have some exercises in the video that is more practical in the lab. So the virtual experience will help you with understanding the association of the basic minerals or most important minerals with respect to the Bowen sequence, and this will help you also with the definition of a name. So again, we revisit this concept. So the color is the most easily observable feature in igneous rocks. It should be relatively easy to describe what you see. It may range from black through dark grays to lighter grays, or actually pink. So these are the most common transition in color. As I stated earlier, content in K-feldspar controls the pink, but then the change in abundance of mafic minerals, we control transition from white to black, basically, or dark. And also remember, the grain size will be critical. Mineral composition, it's important that when we discuss, you list the minerals you can identify in the rock, and I might ask you, if I see something that you have missed, your opinion regarding that specific mineral. Then I might ask you to estimate the percentage of mafics versus felsics, or the percentage of phenocrysts, and in this context it is important that you understand those diagrams about modal abundances. In terms of textures, I think this discussion could vert on the type of texture you are identifying, so if the rock is aphanitic or if the rock is porphyric, and potentially I will ask where the rock formed. So if you have an intrusion that formed at depth and you have a rock that has an equigranular texture, I will ask you and you will tell me that you think it's forming deeper. If I have a basalt with an aphanitic texture, the rock formed relatively shallow, actually in a subaerial condition, most likely. So when we talk about texture, remember to discuss the crystallinity, the granularity of the rock, and also things like the shape of the crystal. So if you remember, we talked about euhedral versus anhedral, and also the subhedral, which is an intermediate term. And maybe I'll ask if you think that the mafic minerals were first to crystallize, or rather the opposite, the felsic came first, like in the example we were seeing of the K-feldspar crystals in that granite earlier. This is an example of how a rock should be described. As part of this lab, you will have an assignment in which you have to describe some photographs of igneous rocks and practice with the nomenclature and terminology that has been illustrated in this laboratory. Remember that you will have in the final phase to attribute a name to the rock, and I have discussed extensively these classifications, so it's important that you familiarize yourself with the Strachan classification for the igneous rocks, and focus really on these classification that deals with rocks that have between 20 and 60% quartz, so the granites, the granodiorites and tonalites, and also look at cyanites, monzonites. So I will give you some example of those. So here we have alkali feldspar granite. Remember when we have quite a bit of alkali feldspar, which is the pinkish phenocryst in this example, and you have quite a bit of quartz, we tend to classify this as an alkali feldspar granite. Here is another example with even more K-feldspar. So granite usually has this characteristic of having quite a bit of K-feldspar and then having also quite a bit of quartz. You can see the quartz here because it's glassy in appearance, and in this particular example we see that we have conditions in which you have either euhedral feldspars, but also other cases in which is either subhedral or anhedral, and the quartz is clearly anhedral. It looks like it's forming veins inside the K-feldspar. So granite is usually common type of intrusive rock, mostly felsic in composition. It will contain dominantly quartz, mica, and feldspar, and usually it's equigranular and phaneritic because of the crystals. They are well developed. You will be able to see the margins of the crystals really well. The rock can be pink, so if lots of K feldspar is present, it will be pink, or get into the gray color if you have more plagioclase entering into play, and also if you have more abundant quartz in the rock. These are rocks that are relatively massive, they're quite competent, so they will be hard and really tough. And the average density will be between 265 and 275, because these are felsic rocks. If we move into the granodiorites, the tendency is to lose the pink color, so easy to spot them because of that, but you still have quite a bit of quartz, so you have usually more than 20% quartz, and we have, at least 65% of the rock that is represented, actually 65% of the feldspar that is represented by plagioclase instead of K feldspar, so the sodic-calcic varieties. So we're talking about albides and also anorthites, respectively, for sodium and calcium end members. Usually it contains abundant biotite, mica, and hornblende, which is the amphibole. So we see usually a drop, progressively a drop in biotite and muscovite in granodiorites when we move to more basic compositions. And usually it does have a darker appearance if compared to a granite because of the abundance of the mafic minerals. You see here how we increase the number of mafic phenocrysts, and this is a tonalite. A tonalite usually have quite a bit of quartz, but we lose completely the K feldspar and also the hydrated phases. So we have less muscovite and biotite. Actually, the rock is almost devoid of these phyllosilicates. And so, by definition, you will have 10% or less alkali feldspar in a tonalite. If we move down in terms of the composition, so we have less than or between 20 and 5% or less than 5% quartz, we enter the realm of cyanites and monzonites, or quartz cyanites or quartz monzonites. And then we have the monzodiorites here and the monzogabbros. So gabbros and diorites are usually rocks that have pretty much all plagioclase. So cyanites will be on the other side, so they will be rocks that are essentially dominated by alkali feldspar. So you see here most of the rock is dominated by alkali feldspar, but you don't see any quartz vein in here, so very little quartz in this rock. So if you don't see quartz, but you have recognized the presence of alkali feldspar, so this is not carbonate, it's not quartz, well, in that case the rock is likely a cyanite. And also, you will have other phenocrysts which will be mafic in composition and will be likely amphibole. So that's also another indication. If you have a lot of biotite in the rock, that's another indication that you are dealing with a cyanite. Monzonites will start to show, a transition. You will have a combination of K feldspar and plagioclase, and so you have a mixture of the two. So you will see a distinction to different feldspars in the rock, and also you will see an increase in the mafic mineralogy. So the proportion or the modal proportion of mafics will be higher in a monzonite. And then you go into, rocks like gabbros, in which you have much more pronounced abundance of mafic minerals. And in this case, we talk about pyroxene. So remember this rule, quite often a gabbro has a composition that is very similar to a basalt. And so it will have like 50% mafics represented by dominantly pyroxene, and the remaining part will be dominated by plagioclase, mostly calcium plagioclase. And these are rocks that are still equigranular, so they will look like an intrusive rock, and they can have either fine grain or coarse grain. This is an example of fine grain crystallization. So this might have been a gabbro that formed relatively shallow, so within the 2Ks, so almost a subvolcanic rock, but if it forms deeper, you can get a very coarse textured gabbros. Here is another example of a relatively mafic rock. So diorite is an intermediate intrusive rock, and it's usually characterized by the abundance of mafics, but quite often you have biotite and hornblende, which helps you with the declassification of these rocks as an intermediate. In particular, the abundance of amphibole. So if you have a lot of amphibole, in that case, it's quite often equivalent to an andesite. So the effusive equivalent of a diorite would be an andesite, and quite commonly you have a kick in the amount of amphibole that will help you with the classification and distinction of diorites. And so this is why it's termed as an intermediate rock. So it's like between a felsic and a basic rock. Sometimes in diorites you will find also small amounts of quartz, so that also is helpful because it's quite rare or actually absent in basaltic assemblages or gabbros. If we are dealing with rocks that are ultramafic, we have to use a different classification. We have seen that during the lectures. So quite often you use the mafic or ferromagnesium minerals to extend the classification. And so the abundance of pyroxene and olivine will help you in this case with the distinction of different ultramafic rocks. So we have gabbros, troctolites, dunites, pyroxenites, so different types of peridotites essentially, and also anorthosites. So when you have more than 90% of the rock composed of plagioclase of the anorthite variety in this particular example. So here you have some of the textures. So if you recall, the diorite is actually up here because of the abundance of plagioclase in the rock. But we have a rock essentially dominated by pyroxene and plagioclase. And so we have a transition field really between gabbros and diorites, which is a function of the percentage of mafics. A pyroxenite will sit at the bottom here, and it will be dominated, so 90% of the rock will be represented by pyroxene, hence the terminology. And then we move on this side, we increase the amount of olivine, and we enter the field of dunites when we have more than 90% of the rock represented by olivine, which has this characteristic green color, which is related also to the nomenclature. So olivine is like olives, and that is the characteristic olive green. Tractolites, we go up and increase the plagioclase content, and you see dramatically a change in the color of the rock, so the white becomes more prominent, and we have a mixture essentially of olivine and anorthosite composition, anorthositic composition, so much more anorthite and essentially much more plagioclase, which will change the appearance of the rock. And ultimately go back to anorthosites, rocks that are quite metallic in appearance, but you can see distinctively the plugs of plagioclase with the characteristic twinning. And so that's your anorthosite rock that contains dominantly plagioclase, but there will be also still either some olivine or pyroxene, which is quite often interstitial, so it's all these dark spots that are present. So you have here a number of specimens that will be considered for your examination. We will discuss some of these in the virtual experience. And here is a picture that represents a summary of the different nomenclature we adopt for the different rocks. We have seen already some of the specimens that there are some additional things like vesicular rocks or other characteristics aspects such as breccias. In this other figure you have some examples of breccias. We will discuss this more in detail in the virtual experience, really. So this concludes this lab on igneous rocks. Again, in the virtual experience, we are going to look at both the intrusive and effusive rocks. So this afternoon, we will discuss these more in detail and try to practice together so that you will be more confident when you have to discuss the rocks with me. I hope this was useful, and if you have questions, feel free to contact me via email, and we will go from there. We have now a forthcoming lab that will be focused rather on the sedimentary rocks, but this will be in a few weeks' time when we have addressed all the lectures that pertain the sedimentary environments and the tectonic settings where we form sedimentary rocks, which are also quite important. So I leave you for a revision of all these terminology about igneous rocks. Remember to check all the diagrams, and you will be allowed to use also a series of classification charts that you will find on the Dropbox linked to D2L. So there is a folder called classification that contains all that additional information that will be helpful, I think, with this type of lab exam, so identification of igneous rocks essentially.